Hi. The last function, or rather family of functions, we're going to cover are trigonometric functions. Well, I'm still going to require some basic knowledge about them from you from high school, but I'm going to try to explain them in as much depth as possible. Okay, so first, trigonometric functions are associated with two geometrical figures. First one is a circle. Imagine that this is a perfect circle. This is as good as I could get. This is why they are also called circular functions. And the second one is right-angled triangle. Right-angled triangle is a triangle which has one 90 degrees angle. Now, what is important for us is the angle over here denoted as theta. Theta is just Greek letter. Get used to it, you will hear more of them over the course. Now, let's first name all the sides in the right triangle. This side closest to the which make between the angle of interest and 90 degrees angle is called adjacent, right? Because it's right next to it. Here you see the opposite because it's on the opposite side of the angle. And finally, the longest side of this triangle is called hypotenuse. Now, we will be denoting them A, O, and H. I will actually need this part of the blackboard, so I will have to erase it. And now let me explain how everything's going to work. Look, imagine that we are going around the circle. And we are going counterclockwise, right? So we are going like that. What is interesting to us is how different ratios of the sides within the circles are going to behave. Okay, and to this end, we're going to start with the sine function. Sine function so sine of theta, or in our case, very soon it's going to be x, is equal to the ratio of opposite, to the ratio of opposite to hypotenuse. Okay, so now we can see how is it going to be behaving. Look, if we start at this position over here, value look, imagine that this side is going, hypotenuse is going all the way down over here. So we see that opposite here is 0. But look, once we start moving up and up and up, we can see that the opposite is going to get bigger and bigger and bigger, and finally, over here is going to coincide with hypotenuse, right? Then we will see that actually, as the hypotenuse moves over here, it's going to start to shrink until we arrive at a place where it's going to be equal to 0. But then look, we're going into negative values over here. And the opposite over here is becoming more and more negative. Where's my orange? Then it gets smaller and smaller and smaller. Finally, we're going to end up over here. What hypotenuse here and opposite are of exactly the same size. And then it's gonna shrink in the last quarter of a circle. Okay, so look, if I would like to start somewhere over here, then how do I look? Look, at the beginning, we know that hypotenuse is 0. I'm sorry, opposite is 0. So 0 divided by hypotenuse will give us 0. And look, this is the point in which we start. Okay, now let me just change this theta to x. And now let's see what is happening over here. Look, now, we know that the full circle has 2 pi radicals, right? So, first quarter of a circle is half a pi. Full circle is pi over, it's just pi. Then we have 3 over 2 pi, which is half a circle, 3/4 of a circle, and 2 pi's is full circle. Right? So now, how should I draw it? Look, we see that as the hypotenuse moves over here, the value of the opposite is getting bigger and bigger and bigger and bigger and bigger. And over here, hypotenuse and opposite are of exactly the same size. So it means that it's equal to 1. So look, we can get the highest value that the sine function can take is 1. Now, what we will observe over later is that now opposite is getting shorter and shorter and shorter until we are over here, when again it's equal, the size of the opposite is equal to 0. Then it starts to grow again, but in the opposite direction. We go to negative values, and here they are of equal size, but this time hypotenuse opposite is negative 1. So it's negative, opposite is negative, so we obtain negative 1. So look, now we can see that that the lowest value sine can take is negative 1. And now, finally, we will see that in this part, as hypotenuse is moving over here, the value of opposite gets closer and closer to 0. And then we've made the full circle. So, summarizing, how should it look? It should look like this. And this is how we make the full circle. And look, if I would be making circles again, I would be getting the same shape again. And also, on the other hand, if I would be moving from the beginning in the opposite direction, I would be obtaining the same shape, but now going in the direction of negative infinity. Okay, so look, this is how the sine function comes about. Now, how can we think about this function? Look, the size of the domain, of course, can be divided into these parts equal to 2 pi. Because like each 2 pi, because like you can imagine that this is your domain, and every time when we make 2 pi, so the angle here is 2 pi, we've made the full circle. We also can notice that the function takes maximum over here at 1, minimum over here at -1. Okay, so this is how we get the sine function. But let's also practice some transformations of this function. And the first one I want to try with you is how would we draw a function sine y equals sine 2x. And these 2x is inside. Okay, look, this means if we've got 2x over here, that, remember, our x is associated with moving counterclockwise around the circle. But now look, before, in order to make full circle, I needed to put 2 pi, right? Instead of x. After 2 pi, I get full circle. Now in this function, if I'm going to plug just pi, I'm going to have 2 pi inside. So what does it mean? Look, as it turns out, when I put a number that is bigger than 1 inside the sine function, I'm like taking and squeezing it in. Because now look, this function is making full circle twice as fast. So how will we see it? And look, this function is doing full circle in pi, and within 2 pi's it's making 2 circles. So we could see that now periodicity of this function changed. Now it's now it takes x twice as much less time than before. So the function is being squeezed, right? So here we would have the same thing. Here we would have half a circle. Here we would have a full circle. And basically, this is how this transformation works. Every time when I put here a number that is bigger than 1, the function is being squeezed. But what about if we would put here a number that is somewhere between 0 and 1? So look, now if y would be sine 1 over 2, x over 2, what does it mean? Look, now if I put 2 pi over here, I will be able to make just half a circle. So now the function is spreading, and we would see that as now within 2 pi's, I would be able to make just half a circle. So look, and if I'm going to put 2 pi over here, I'm going to put pi. So now the function has spread out. Okay, so I think this is enough about sine. Now let's go to cosine. And actually, once we know how to draw sine, making cosine is going to be fairly easy. Okay, so first we've got cosine. Oh, I'm already going to write this, but you know that it's associated with theta. And now the opposite, we need to have adjacent, and adjacent was orange. Okay, so adjacent divided by hypotenuse. Okay, and look, let's just see again what is happening. Now, at the very beginning, if we are over here, hypotenuse and adjacent are of the same size. So we should start at 1. But then look, as we go here, we see that adjacent is getting smaller and smaller and smaller. And after half a pi, it reaches just 0. Then it starts increasing again. And it starts increasing again. And now have the same size as it has the same size as hypotenuse. But now we remember we are in negative values, right? We went below 0. Then it starts to shrink in absolute value and gets to 0 here. And finally it starts to increase again. So we clearly see that it will have the same range of values as sine, right? Okay, if we have y here, x here, so the range of values will be 1. And from negative 1 to 1, right? Now, let's put some. We need to have pi over 2, pi, 3 over 2 pi, and 2 pi. That should be enough. Okay, so how should I draw it? Now, look, we started from the position of 1, so now it's shrinking to 0, and then after half a circle, remember, we reached negative 1. And then, look, then we just need to finish the full circle. And this is how cosine comes about. Okay, now, how can we make some other transformations? Okay, let's just say that now we've got a function y equals 2 cosine x. Look, basically what we do over here is we multiply each value by 2. Okay, so let's just say that I'm going to denote 2 over here and negative 2 over here. So, also, because we know that if the highest value used to be 1, now it can be 2. The lowest, negative 1, now it's going to be negative 2. And 2 times 0, still 0, right? So, zeros are going to stay in the same locations. So, how should I draw this function now? Okay, I hope you can see that the function just got wider. It has the same periodicity because we still go through all appropriate points at the same time, but now it takes bigger or lower values depending whether we are on the positive or negative, on negative side or of x axis. And look, what if now I would like to do a function y equals 1 over 2 cosine x? Well, I hope at this moment you can see this is nothing very problematic. We have to make an asymptote on 1 over 2 and negative 1 over 2. And then we just need to draw the function exactly the same as this one, just with the same periodicity. We would just go on lower values. Okay, now, So we basically covered sine and cosine. We're going to cover, of course, here for now just 4 basic functions. So now let's go to tangent and cotangent. Okay, so tangent, I'm already going to write x, and tangent x is equal to opposite, and which color was, where is my, I'm sorry, I lost my orange color, so, here it is. Okay, so, and again, this is opposite divided by adjacent. Okay, well here the situation is not as clear cut, but I hope we're gonna see what I'm trying to say quite easy. Okay, so look, again we are starting here we have y, here we have x, and we start at 0. Look, what is the value of this ratio at 0? Well, look, opposite is equal to 0, adjacent is equal to hypotenuse, so this is 0. But look, what's going to happen then? We see that as we are moving over here, the opposite is getting bigger and adjacent is getting smaller. It's getting smaller and smaller and smaller. And look, here is the problematic part, right? Once we've got here, we need to divide by 0. And division by 0 is prohibited. So what should I do? At pi over 2, I should create an asymptote. Because at this place, I just cannot divide. So function is undefined. Okay, now let's do something a little bit different. But now let's go in the opposite direction. Look, again, here we will see that opposite is getting bigger while adjacent is getting smaller until the point where we need to divide by 0 again. So at pi, negative pi over 2, again the function is undefined. So how will it look in between? Well, we see here that the function is growing, and because there are two forces, on one hand, opposite is getting bigger, adjacent is getting smaller, this function is actually growing faster and faster and faster. And over here, we will actually see that at the beginning, that here, actually, if we would move over here, then we also see that the function would be, because over here, both adjacent is declining and opposite is increasing, the function will also be declining faster and faster. So the shape we are obtaining is over here. Okay, so now let's see what happens in this part of a circle. Right? Look, in this part of a circle, we started with something we couldn't have, right? Because this is pi over 2. And but what is happening over here? Look, now adjacent is becoming negative, and opposite is becoming smaller and smaller and smaller. So the value here again should be negative, and it should be getting closer and closer and closer and closer to 0, right? And over here, what will we have? Now the adjacent is at hypotenuse side, and then we're getting two negative values because adjacent is negative, opposite is negative, which gives us a positive value. So before we get to when we get to pi, 3 pi over 2, we will see again obtain the shape like this. And look, for this reason, the tangent function looks like that. And the same will be here. And look, we can make the same transformations as we did before. Look, let me just show you one example. If we have, for example, y equals 2 tangent x, what will we have? We will have a function that is twice as steep. So, it will look like this, and like this. 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 What about periodicity? Look, now, each time, if we include, if I would put 2 in front of x, we would make a circle twice as fast, but we would have twice as many points that we need to exclude from that domain of the function. Okay, and finally, the last function we're going to cover is cotangent x, and all we gotta do to get cotangent is to reverse things in the denominator. It's to get reciprocal. So now opposite is gonna be here, and I have a problem with this adjacent with orange one. Yeah, okay. And look, now when we are dividing in opposite way, we're gonna actually have a problem at the very beginning. Because look, here opposite is 0. So we can imagine again that here is an asymptote covering vertical axis. Then what is happening? Opposite is getting bigger and bigger and bigger, while adjacent adjacent will be getting smaller and smaller and smaller, while the opposite gets bigger and bigger and bigger and bigger. But over here, adjacent will take it will be getting smaller and smaller and smaller and smaller, while this will be getting bigger and bigger and bigger. So remember, we are getting one number which we decrease, and we are dividing by a bigger and bigger and bigger number. So this function should be falling, and it does so right until pi over 2. What's happening in the next corner of a circle? Look, here adjacent is getting bigger, but it's negative in absolute terms, but it's becoming more and more negative, while the opposite is getting smaller and smaller and smaller. And over here again we need to divide by 0. So at pi we will have another asymptote, and this is the second part of the cotangent. And look, as you might expect at this moment, this function is also periodical. So here we will have 3 over 2 pi. Here we will have 2 pi. And we can make the same one over here. Negative pi over 2, negative 3 over 2 pi. Okay, and I think this is it about trigonometric functions. In the next video, I'll try to summarize them. Okay, thank you for your attention.